Welcome to the deep dive. We're really thrilled to have you with us today. I want to kick things off right away with a little thought experiment for you.
Oh, I love these.
Yeah, so I want you to mentally walk through your typical day, right?
Yeah.
But pay close attention to the background objects that you usually just filter out. So picture that incredibly ordinary metal gondola shelf holding up boxes of cereal at your local pharmacy.
Okay, got it.
Now picture a piece of heavy construction equipment, so maybe a bright yellow excavator parked seemingly at random in a dirt lot near a highway interchange. And then finally, look up into the sky and just imagine the invisible, completely chaotic cloud of spent rocket boosters and defunct satellites. The space junk orbiting in the thermosphere right above your head.
The stuff we never see.
Exactly. So what if I told you that the shelf, the excavator, and the space debris aren't just random objects? What if they could be interconnected nodes in a massive, completely untraceable, and highly localized global communication network?
I mean, it sounds like the setup for a high-concept espionage thriller, but the really crazy thing is that the underlying engineering is entirely grounded in current physics and legal frameworks, actually.
Yeah.
Today, we're analyzing a really dense, highly unusual source text. We're looking at the literal filed blueprints for what the author considers the next generation of information warfare and covert infrastructure.
We really are. We are digging into a massive compilation titled The Architecture of Control. So this is a 2026 compilation of real patent applications submitted to the U.S. Patent and Trademark Office. And it's by R.J. Aguar.
Yeah.
Our mission for this deep dive is to deconstruct these patents for you. We want to decode what they actually propose for the future of covert communication, optical computing, and really how the physical spaces we navigate every day are being repurposed. But before we get into the technical weeds of these systems, we have to talk about the origin of this text.
We do, because it is definitely not a standard corporate filing.
Not at all. The author has a very specific background that informs all of this engineering.
Right. The author is a former Google search ranking engineer who is currently operating under protected refugee status, specifically citing the 1951 Refugee Convention. He didn't compile these patents to launch a startup or, seek venture capital. He compiled and published this entire volume as a defensive publication.
Okay, let's unpack this.
Yeah.
Because a defensive publication means he is intentionally putting incredibly advanced, potentially weaponizable communication architectures just directly into the public domain.
Yeah, that is the core legal strategy here. His stated objective is to preempt state-sponsored actors, or just really heavily funded surveillance corporations, from silently patenting these technologies for their own exclusive covert use.
Because once they own it, they hide it.
Exactly. In intellectual property law, by publishing the mechanics of these systems comprehensively, he establishes them as prior art. And once it is prior art, it becomes legally impossible for any subsequent entity to claim they invented it first. So no government or corporation can lock the technology away behind a classified patent. The text basically functions as a legal barricade. It's engineered to burn the ground ahead of heavily resourced intelligence apparatuses.
Which really sets the stakes for everything we are about to discuss today.
Right.
The driving philosophy behind the first section of the book is this idea of operational security in a panopticon.
Right.
If we assume an adversary is monitoring the entire electromagnetic spectrum, like if they have deep packet inspection on the internet and they're logging every single handshake between a cell phone and a tower, how do you actually communicate? I mean, you can't just use Signal or a VPN.
No, you can't. The text argues that in an era of absolute digital surveillance, encryption is just no longer sufficient. If an intelligence agency is relying on traffic analysis, they don't necessarily care about the contents of your message.
The metadata is the message.
Yeah, exactly. If you send a beautifully encrypted, totally unbreakable message from your device to my device, the network still logs that an exchange of data occurred between our two IP addresses at a specific millisecond, containing a specific payload size. That metadata alone is often enough to establish a relationship and compromise a network.
Right, so the author's thesis is that true operational security requires abandoning conventional routed networks completely. The communication literally must be physically decoupled from the grid.
It has to be analog in a way.
Which takes us to the first patent in the compilation, moving from the digital realm back to physical infrastructure. So let's look at the concept of the modern dead drop.
This is fascinating.
It is. The author proposes using those metal retail gondola shelves I mentioned earlier as the housing for a localized asynchronous communication node. But my immediate question when reading this was about the radio frequency profile.
Right, the RF signature.
Yeah, like if an operative is dropping a digital transmitter inside a pharmacy, Isn't that just creating a new RF signal for an adversary to detect with a software-defined radio scanner?
And that is exactly where the structural geometry of the retail shelf becomes critical to the patent. The author isn't suggesting hiding a powerful Wi-Fi router behind a box of cereal. He specifies utilizing small, self-contained units equipped with a memory module, a battery, and a strictly short-range transceiver.
Like Bluetooth or something.
Specifically, near-field communication or ultra-low-power Bluetooth Low Energy, BLE. And the device is placed physically inside the hollow, non-visible structural columns of the metal gondola shelf itself.
So the shelf itself is actually participating in the physics of the transmission.
Yes, the metal casing of the shelf acts as an imperfect Faraday cage. It severely attenuates the already weak RF signal propagating from the BLE or NFC chip. So the transmission bubble is deliberately constrained to perhaps a radius of 10 to 15 centimeters from that specific metal strut.
Wow, so it's tiny.
It's microscopic in radio terms. If counterintelligence is sitting in a van in the parking lot with high-gain antennas sweeping for anomalous RF emissions, the signal is completely buried beneath the noise floor of the building's ambient electromagnetics. You cannot detect it unless your receiving antenna is physically within inches of the specific shelf column.
Okay, so mechanically, Operative A walks into the store. They are posing as a shopper. They stand in front of the specific shelf. Maybe they're inspecting a product to justify their physical proximity to the column. Their smartphone or some custom device handshakes with the hidden node via that tightly constrained Bluetooth or NFC field. They push the encrypted data payload to the node's local memory, and they simply walk out of the store.
And the critical security protocol here is the asynchronous decoupling. Operative B, the receiver, does not enter the store until hours or perhaps days later. They perform the exact identical physical maneuver: shopping, hovering near the shelf, initiating the short-range handshake, and pulling the data from the node.
And the patent notes that the node instantly initiates a cryptographic wipe of its memory the millisecond the download is verified.
Right. By severing the transmission in time, you completely defeat traditional traffic analysis. There is absolutely no digital connection bridging Operative A and Operative B. They never connect to the same cell tower at the same time. They never exchange packets across an ISP.
Their only connection is sequential physical proximity to a static, mundane piece of commercial infrastructure.
Exactly. The adversary would have to run continuous, manual physical surveillance on every single aisle of every single retail store to correlate the movements of the two operatives.
It's an analog loophole for digital data. It's brilliant.
Mm-hmm.
But as clever as the retail shelf is, it does require physical access. The second patent in this section deals with a much harder target. How do you extract data from a computer that is completely disconnected from the internet?
The air-gapped machine.
Right. We're talking about the invisible optical screen side channel. If a target machine is air-gapped, so no Wi-Fi card, no Ethernet cord, it's just sitting in a secure room.
Mm-hmm.
How is this malware actually getting the data out? It can't use radio waves, so what is the escape route?
The patent details a highly sophisticated optical exfiltration method that leverages the target's own display hardware. The text outlines a scenario where the target machine has been previously infected, perhaps through a compromised hardware supply chain or, a malicious peripheral like a USB drive.
Sure.
The malware's job is to read the sensitive files on the local drive and translate that binary data into microscopic modulations of the computer monitor's output.
Okay, let's get into the mechanics of that modulation, because this is where my skepticism really kicked in. The patent claims this modulation is completely imperceptible to the human eye. If I am sitting at my desk looking at my monitor, how am I not noticing that my screen is transmitting data like a frantic Morse code lamp?
It comes down to human biology versus sensor physics. The human eye has a relatively slow critical flicker fusion rate. If a light source blinks faster than roughly 60 frames per second, the human brain just smooths it out into a continuous beam. Furthermore, the human eye is notoriously bad at detecting minute shifts in color luminance, especially when you're focused on the content of a screen, like reading text or watching a video.
You're just not looking for it.
Right. And the malware described in the patent does not flash the entire screen black and white. It targets a microscopic region, perhaps just a cluster of 4 pixels down in the corner of the taskbar.
So it's manipulating the specific red, green, or blue subpixels.
It modulates the intensity value of those specific subpixels by perhaps 1 or 2%. A blue pixel might shift from a color value of 255 down to 252 for a duration of maybe 8 milliseconds, which is a single frame on a 120 Hz monitor, and then it returns to normal.
And to me, reading a document on that screen,
Nothing happened. Your optical cortex filtered out the variation as electrical noise or simply missed it entirely.
but if the variation is that incredibly subtle, how does the receiving device pick it up? Because the text mentions embedding a covert sensor in a coffee mug on the desk, or a power adapter plugged into the wall behind the user. How does a sensor in a coffee mug isolate a 2% shift in a single pixel across a brightly lit office?
Well, the covert receiver is equipped with a high-speed photodiode and a highly specific optical bandpass filter. While the human eye takes in the entire spectrum of visible room light, the sensor is optically tuned to look only at the very specific narrow wavelength of light emitted by the monitor's LED backlight or OLED array, and it samples the ambient light in the room at thousands of hertz.
Wow, so it's functioning way above the Nyquist rate of the monitor's refresh cycle.
It is drastically oversampling the environment. Because it is sampling so fast, it can mathematically subtract the steady 60 Hz hum of the overhead fluorescent office lights, isolate the high-frequency microflickers coming from the screen, and decode those tiny variances back into a binary stream. The elegance of the attack really is that it requires absolutely zero hardware modification to the target machine.
The malware just hijacks the graphics processing unit that's already there.
It utilizes the existing trusted peripheral, the monitor, as the transmission vector. Standard cybersecurity protocols are completely blind to this. An endpoint detection system is looking for unauthorized network packets, or anomalous memory allocation, or sudden bursts of radio frequency. It is not programmed to care if the user's desktop background pixel shifted its gamma curve by 1%.
It just ignores it.
Yeah, the data flashes right into the open air of the secure room, totally silently.
It's terrifying, honestly, because it weaponizes the very thing you use to interface with the machine. But the author doesn't stop at the scale of an office desk. In the second segment of the source material, the patents scale visual steganography up to a planetary level.
Yeah, we move from the micro to the macro.
Let's move outdoors and talk about using the entire world as a billboard for satellite communication.
This section transitions from localized tactical operations to strategic over-the-horizon intelligence gathering. The core problem this architecture addresses is transmitting high-value, low-bandwidth data from deep within hostile territory, where transmitting any radio frequency signal is basically a death sentence.
Right.
If an operative turns on a satellite phone in a heavily monitored zone, signals intelligence will triangulate the emission source in seconds, leading to an immediate kinetic strike or capture.
So the goal is zero emission communication. The operative has to send a message to a satellite orbit in low Earth orbit without broadcasting a single watt of electromagnetic energy.
Yes.
The patent solution is arranging large physical objects on the ground, like shipping containers or heavy construction machinery in open areas like an industrial lot. But from a satellite's perspective, looking down through atmospheric distortion, how does an algorithm differentiate a truck from a large rock or a shadow or just general environmental clutter?
That is the central challenge of remote sensing and computer vision. If you simply park a gray sedan in a gravel lot, the contrast ratio is terrible. The satellite's imaging sensor, even at a high ground sampling distance resolution, is going to struggle to cleanly isolate the asset from the background noise.
Right, it just blends in.
So the author's solution is to exploit the specific spectral signatures of legally protected industrial paints. He specifically cites the use of trademarked colors.
He mentions Caterpillar yellow and John Deere green. I found this to be one of the most brilliant lateral thinking solutions in the entire book. Why does trademark law matter to a satellite?
Because nature does not synthesize Caterpillar yellow. The chemical composition of those industrial paints creates a highly unnatural, incredibly specific spectral reflectance curve. When a computer vision algorithm, something akin to a massive parallelized YOLO object detection model processing the satellite telemetry, is scanning millions of square miles of imagery, it doesn't have to look for the shape of a tractor.
Oh, wow.
It simply applies a hard mathematical filter for that exact nanometer wavelength of yellow.
It creates an enormous signal-to-noise ratio. The algorithm just drops out all the greens of the trees, the grays of the concrete, and the browns of the dirt. The only thing left glowing on the data map is the legally protected paint job of the excavator.
And the trademark aspect is a secondary layer of operational cover. If an adversary questions why an operative has a massive, brightly colored machine sitting in their yard, the operative has perfect plausible deniability. It is standard construction equipment. Its color is mandated by corporate branding, not intelligence requirements.
Okay, so the satellite's algorithm has successfully filtered the noise and isolated this bright yellow excavator in a dirt lot.
Yeah.
How does that object actually convey complex data? The patent breaks down the communication protocol into geometric states, specifically focusing on symmetry versus asymmetry.
The protocol must be readable regardless of the viewing angle of the satellite. A highly symmetrical object, perhaps a circular water tank or a truck with a large, perfectly round logo painted on the roof, functions as a simple binary indicator.
A Boolean state.
Exactly a Boolean state. The mere presence of the symmetrical object in a predefined geographic grid square equals a 1. The operation is live, the target is acquired. If the grid square is empty, the state is 0. It is a very low bandwidth ping.
But Boolean states aren't enough to run a complex operation. I mean, if you need to send instructions or highly specific status updates, you need way more data density. That's where the asymmetrical objects come into play, right? The text uses the example of an excavator with a long mechanical boom arm.
Right. An asymmetrical object allows the operative to encode data using the rotational orientation of the asset. Because the object has a clear front and back, or a distinct longitudinal axis, the satellite imagery can determine its precise compass heading. By physically parking the excavator and rotating the cab so the boom arm points precisely north, the operative encodes a specific vector.
So you basically build a protocol matrix. Pointing north at 0 degrees means proceed to extraction point alpha. Rotating the cab to point east at 90 degrees means target has moved standby. By manipulating the yaw of a single mundane piece of machinery, you're essentially turning a 20-ton vehicle into a dial on a massive analog modem.
The bandwidth is incredibly low. You are transmitting mere bits of data per satellite pass, but the security is absolute. There is no radio wave to intercept. There is no encrypted packet to crack. The message is entirely structural.
But if you scale this up, like if you have intelligence networks constantly moving yellow excavators and gray sedans around a city to communicate, wouldn't an adversary's counterintelligence eventually notice the pattern? I mean, if every time a white delivery van parks facing south an embassy gets compromised, machine learning models will eventually flag that physical behavior.
The author anticipates this behavioral analysis vulnerability, actually, and he introduces a command and control architecture called dynamic asset sharding. The goal is to completely decouple the physical asset from any predictable long-term operational pattern. The system utilizes a two-tier sharding protocol.
Walk us through the math of this sharding. How does a handler organize a fleet of these physical encoders without generating a recognizable pattern of life?
The first tier is object sharding, which is strictly deterministic. The algorithm groups the physical assets based on immutable static features. For example, the software categorizes every gray four-door sedan within the operational theater into Shard A. Every white commercial panel van is assigned to Shard B.
Okay, so that organizes the inventory, but it doesn't solve the pattern problem.
Right.
If Shard A is always doing surveillance, it's still predictable.
Exactly, which is why the second tier, function sharding, is the core innovation. The system does not statically assign roles. Instead, it dynamically assigns the operational function of each shard using a complex time-variant function. The system might use modulo arithmetic based on the current Unix epoch time, or a pseudo-random number generator seeded by a pre-shared key to constantly shuffle responsibilities.
So the role changes day by day or even hour by hour.
The algorithm dictates that on Monday, Shard A, all those gray sedans, are designated as the active visual encoders for the satellite network. They must park in specific orientations. But on Tuesday, the time variant function shifts the roles. Shard A is now strictly relegated to passive logistical transport, and Shard C, perhaps a fleet of municipal garbage trucks, suddenly becomes the active visual signaling layer.
Wow, so if hostile counterintelligence is trying to train a machine learning model to track the gray sedans, the data set is constantly being poisoned. The physical behavior of the assets is constantly morphing, looking like random logistical noise to anyone without the cryptographic seed driving the time variant function.
And the author provides some highly evocative examples of how these dynamically assigned visual encoders would look in the wild. One scenario describes an operative acting as a landscaper. They use an open-air flatbed trailer and arrange specific models of brightly colored riding lawnmowers in a grid pattern. The presence, absence, or specific model of a mower in a particular quadrant of the trailer forms a literal visual barcode for the passing satellite.
Another one I found fascinating was using a highly asymmetrical sports car, vehicle with a very long hood and a short trunk deck, parked in a large semicircular driveway. The precise angle at which the car is parked off the center axis of the driveway encodes a mathematical vector for a completely different operational team located miles away. It tunes the entire urban landscape into a read-only memory board.
It really is a radical reimagining of urban space. However, any visual steganography system reliant on passive optical satellites faces a fundamental physics problem, the diurnal cycle. What happens when the sun goes down? Standard electro-optical sensors on a satellite are completely blind in the pitch black.
You can't see the trademarked Caterpillar yellow paint at 2:00 a.m.
No, you cannot. The patent addresses this limitation through a methodology termed islands of light. The operatives must exploit existing high-intensity public infrastructure. The text details operations centered around pre-lit environments, specifically using the example of municipal athletic fields equipped with stadium lighting.
The power output of those lights is massive. They generate enough lux to push through the atmospheric column and register cleanly on the satellite's imaging sensor, even with a super short exposure time.
And the operational cover is brilliantly mundane. A team of operatives poses as members of a local soccer or football league running a late-night practice. Under the intense glare of the stadium halogens, they utilize the brightly colored equipment inherent to the sport. High-visibility orange training cones, or even their own uniquely colored practice pennies and uniforms.
So while they appear to be running passing drills, they are actually organizing themselves into specific geometric arrays on the turf. They become human pixels. The satellite passes overhead, captures the illuminated grid of the athletic field, and decodes the spatial arrangement of the orange cones and blue jerseys. It allows the zero-emission network to function 24 hours a day.
But all of this visual data, the excavators, the lawnmowers, the training cones, is completely meaningless to the receiving command center unless they possess the correct cryptographic key to decrypt the matrix.
Right, of course.
If a yellow tractor pointing north means proceed, you need the key to know that.
And you cannot transmit that key over the internet, or you defeat the entire purpose of the zero-emission air gap. The patent outlines a highly complex two-factor method for secure key distribution that relies on geographic manipulation.
The author describes a geo-relocated seed protocol. Distributing a cryptographic key via a single channel is a single point of failure. This architecture requires two separate transmissions utilizing two entirely different physical mediums occurring in two distinct global locations.
Break down the math of how these two locations interact, because this part was a bit dense.
Okay, so the key is split. Part 1, which the text calls the visual seed, is transmitted via the satellite visual encoding network. Perhaps it is a specific arrangement of maritime shipping containers in a port in Europe. Part 2, the local seed, is transmitted via a localized physical encounter, much like the short-range NFC protocol we discussed with the retail shelves. An operative in a passing car pings a hidden receiver embedded in the wall of a building in North America.
So to intercept the key, an adversary's intelligence agency would have to simultaneously possess real-time high-resolution satellite imagery of the specific European port ADD, have an agent standing on the correct street corner in North America with an NFC scanner at the exact right millisecond.
That alone makes interception highly improbable. But the true genius of the protocol is how it eliminates the need for a vulnerable central database. A handler doesn't have a spreadsheet listing where both halves of the key are located. The locations are mathematically entangled.
The text uses the concept of a rigid transformational rule.
Yes. The geographic coordinates of location A dictate the coordinates of location B. The author provides a simplistic example of negating the longitude. Imagine the local seed is transmitted via NFC at a safe house located exactly at -95 degrees longitude in North America.
Okay.
By applying the mathematical transformation, flipping the negative to a positive, the protocol dictates that the visual seed must be transmitted at +95 degrees longitude, which places it deep within the Asian continent.
The math creates the map. If you know the location of the safe house and you know the mathematical rule, you instantly know where to point the satellite to find the second half of the key. But an adversary who only discovers the safe house has no way of knowing which mathematical transformation out of millions of possibilities is being applied. They have no database to hack. The security is baked into the geography itself.
It is an incredibly robust, multi-layered architecture. But the author's ambition extends far beyond the atmosphere. In the third segment of the compilation, we reach what I consider the most technically audacious and computationally punishing concept in the entire text. We are moving from utilizing physical infrastructure on the ground to weaponizing the orbital mechanics of space debris.
Here's where it gets really interesting. The patent outlines a methodology for creating an over-the-horizon communication network using passive reflection off non-cooperative orbiting objects. Before we get into how insane the math is here, let's establish the fundamental problem. If I'm in an operative base in the mountains of Central Asia and I need to transmit a massive data file to a command center in Washington, D.C., I cannot point a radio antenna at the sky and just transmit. The Earth is a sphere. The radio waves will just shoot off into space.
To establish a link over the horizon, you require a relay. Historically, this meant relying on highly vulnerable undersea fiber optic cables or bouncing signals off the ionosphere, which is heavily dependent on weather and solar activity, or utilizing dedicated cooperative communication satellites like the Starlink constellation or military SATCOM networks.
But the author points out that dedicated satellites are massive targets. They're expensive, their bandwidth is monitored, and in a peer-to-peer conflict, they will be the first things targeted by anti-satellite weaponry. The cooperative infrastructure is a liability.
The author's solution is to abandon the need for a cooperative receiver in orbit entirely. He proposes utilizing the tens of thousands of existing objects in low Earth orbit. Defunct weather satellites, spent rocket boosters, dead telemetry arrays, and large fragments of space junk. Not as active transponders, but as completely passive physical mirrors.
You don't hack the dead satellite. You don't try to turn its power on. You simply fire a highly focused, high-energy radio frequency beam from the ground, bounce it off the metallic chassis of the space junk, and angle it so it hits the receiving station on the other side of the planet. It's like playing billiards with a laser pointer and a mirror. But the mirror is flying at roughly 17,000 miles per hour through the thermosphere.
The physics concept is specular reflection. The radio wave hits the metallic surface of the non-cooperative object and reflects at an angle equal to the angle of incidence. The challenge is not the transmission power, it is the geometry. You are attempting to solve an immensely complex four-dimensional kinematic problem.
Walk us through the variables of that kinematic problem. Why is it so difficult for a computer to predict this bounce?
You're dealing with three spatial dimensions and the dimension of time applied to objects moving at orbital velocities. To calculate a viable bounce, the system's computational engine must possess the precise location of the transmitting antenna, the precise location of the receiving antenna, and the exact real-time trajectory of the orbiting piece of debris. Furthermore, the system must calculate atmospheric refraction, how the radio wave bends as it exits and re-enters the Earth's atmosphere.
Where does the system even get the data to track tens of thousands of pieces of random space junk?
It ingests public astrometric data. The United States Space Surveillance Network tracks objects in orbit and publishes this data in a format known as two-line elements, or TLEs. A TLE is a data string that defines the Keplerian orbital elements of an object for a specific point in time known as the epoch. It includes variables like the orbital inclination, the right ascension of the ascending node, and the mean anomaly.
So the system downloads the TLEs for 20,000 pieces of junk. How does it crunch that data fast enough to actually execute a transmission? Because if it takes an hour to calculate the math, the piece of space junk has already orbited the planet.
The author actually proved the computational viability of this architecture. He didn't just write a theoretical patent. The text includes the architectural blueprint and source code for a functional prototype. He built a distributed cloud-based engine using Python, leveraging the Flask web framework to manage API requests, and a highly specialized astrometric library called Skyfield.
I want to dig into that prototype. How does Skyfield actually solve the four-dimensional problem?
Skyfield is a pure Python astronomy package that implements the SGP4 orbital propagation algorithm. SGP4 takes those two-line elements and mathematically propagates the orbit forward or backward in time, allowing the system to predict exactly where a specific piece of debris will be in the sky relative to a ground observer at any given millisecond.
But running the SGP4 algorithm for 2,000 objects simultaneously to find the one perfect geometric alignment would crash a standard computer.
Which is why the author engineered a task queue architecture. The central Flask server does not compute the math itself. It acts as a dispatcher. It takes the massive data set of TLEs, breaks it into hundreds of smaller batches, and pushes those batches into a message broker like Redis or RabbitMQ. Hundreds of individual virtualized worker nodes, perhaps scattered across an anonymous cloud computing cluster, pull the tasks, run the SGP4 calculations in parallel, and return the geometric solutions to the central server.
It's massive parallel processing. And the text claims this architecture can calculate a viable bounce solution, finding the perfect piece of space debris out of a catalog of thousands in under 30 seconds.
30 seconds to provide what the patent calls a firing solution. Once the engine finds a viable piece of space junk that will perfectly intersect the line of sight between the transmitter and receiver, it must actuate the hardware. The text details two distinct implementation methods on the ground: movable antennas and fixed antennas.
Let's start with the movable antennas. This seems like the more intuitive approach.
With a steerable parabolic antenna array, the computational engine provides the hardware controller with highly specific targeting telemetry. It calculates the required azimuth, the exact compass bearing, and the required elevation angle off the horizon. The system initiates a countdown. The physical motors of the antenna slew the dish to the exact coordinates, tracking the invisible dead satellite as it streaks across the sky and fires the high-energy RF burst at the precise millisecond of geometric alignment.
It works. But steerable antennas are problematic in a covert scenario.
Right.
They are mechanically complex, the motors can fail, and a massive dish physically moving to track the sky is incredibly obvious to overhead optical surveillance. It generates a massive physical signature.
That vulnerability leads to the second and far more elegant hardware implementation: the keyhole search utilizing fixed arrays. In this configuration, the transmitting and receiving stations utilize phased array antennas or static parabolic dishes that are permanently locked into cardinal directions. For example, the transmitter might have four antennas permanently pointing north, south, east, and west, locked at a 45-degree elevation. The hardware never moves.
So if the antenna can't move to track the space junk, the math has to do the heavy lifting. The computational engine has to wait for the universe to align.
Precisely. The computational engine fundamentally reverses its approach. Instead of calculating where an object will be and aiming at it, the software defines a rigid mathematical keyhole in the sky. This keyhole is the exact conical volume of space illuminated by the fixed beam of the transmitting antenna. The system runs the SGP-4 propagator on the entire orbital catalog, searching for a single object whose predicted trajectory will take it exactly through that invisible static cone at the exact moment its geometry allows the signal to reflect into the static cone of the receiving antenna thousands of miles away.
The system just sits there crunching numbers until it finds a piece of junk flying through the exact center of the crosshairs. When it finds a match, it doesn't move a motor. It just sends a timestamp to the transmitter. Fireburst transmission at 14.02 and 33 milliseconds.
And the signal bounces off a piece of a 1990s weather satellite and hits a receiver on another continent. The implications for signal interception are staggering. This architecture provides an almost entirely ephemeral communication link.
If an adversary is trying to intercept this data, they are looking at an impossible task. They don't know which of the 20,000 objects in orbit is being used as the mirror. The reflection point isn't a geostationary satellite parked over the equator. It is a piece of debris moving at Mach 22, and the node changes for every single transmission. The bounce point is transient. It exists for a fraction of a second and then it's gone. It makes traditional SIGINT interception practically mathematically impossible.
It is the ultimate evolution of operational security. But the source material does not merely rest on communication protocols. The final segment of the book represents a massive foundational pivot. The author moves from manipulating radio waves and physical objects into the realm of advanced material science, optical computing, and the geopolitics of intellectual property law. We have to analyze the CVBNI technology.
CVBNI stands for High Bandwidth, Low Latency Optical Data Cable. The text frames this not as an incremental improvement, but as a paradigm-shifting hardware solution designed to break what is widely known in the industry as the quantum bottleneck. Before we discuss how CVBNI works, let's establish the baseline. Quantum computers are processing data at scales that shatter classical computing models. What is the actual physical limitation holding them back?
A functional quantum computer operating with highly entangled qubits generates what the author accurately describes as classically unmanageable datasets. The sheer volume of simultaneous state calculations produces a tsunami of output data. The processing core itself is not the limitation. The limitation is the physical network required to extract that data and allow multiple quantum nodes to communicate with each other.
The current standard for high-bandwidth data transmission is serial fiber optic cable.
Yes, and a serial fiber optic connection, regardless of how advanced the modulation protocol is fundamentally constrained. You are transmitting data linearly. It is a sequence of lead pulses representing binary states, ones and zeros. You can increase the frequency of the pulses, you can multiplex different wavelengths of light down a single fiber, but it remains a sequential serial process. It is a single lane of traffic trying to accommodate the output of a quantum superhighway.
The CVBNI patent proposes abandoning the serial transmission model entirely. It introduces the concept of massive parallel optical interconnects.
The author redesigns the core architecture of the data cable. Instead of utilizing a single laser diode pulsing down a fiber core, the CVBNI system utilizes microscopic digital displays, spatial light modulators at the transmission interface. You can envision it as an ultra-high definition micro LED or OLED screen, microscopically scaled down to fit the diameter of a data cable connector.
Let me try an analogy here to ground the mechanics. Imagine the data output of a quantum processor is a massive chaotic crowd of millions of people trying to travel from New York to Washington, D.C. A standard fiber optic cable is like a single, incredibly fast bullet train track. You can only load one train at a time. The CVBNI technology demolishes the single track and replaces it with a million parallel highways.
The analogy is robust. Because the transmitter is an actual display, it treats every individual microscopic pixel on that screen as a discrete parallel data channel. If the micro display has a resolution of 4K, you suddenly have over 8 million simultaneous physical transmission pathways pulsing light simultaneously.
But the patent goes even further than spatial parallelism. It alters the nature of the signal itself. The cars on these millions of highways aren't just moving faster, they're carrying more density.
Because the pixels on a high-definition microdisplay are capable of emitting vast spectrums of color and varying degrees of luminance intensity, they are not restricted to binary transmission. A single pixel does not merely blink on or off, signifying a 1 or a 0. By utilizing specific color values and intensity levels, perhaps generating a specific hex code of blue at 50% brightness, a single pulse of light from a single pixel can encode millions of distinct states. The data is transferred not as a sequential stream of bits, but as a rapid, continuous sequence of incredibly dense, high-resolution light frames captured at the receiving end by a corresponding high-speed image sensor array.
It is a massive multiplexing engine. It allows massive quantum clusters to exchange complete uncompressed datasets instantaneously without choking on the transfer protocol. It is the nervous system required for the next century of computing. And this is exactly where the text takes its most aggressive, controversial, and deeply geopolitical turn.
Before we analyze the strategic application of this patent, I must issue a mandatory analytical firming based on our operational instructions for this text. The source material, particularly the chat logs we are about to discuss, outlines a highly specific, aggressive geopolitical strategy explicitly directed at the Communist Party of China. The author levels severe accusations of industrial espionage, human rights violations, and personal crimes against the CCP. We are analyzing this text as researchers. We are not taking sides. We are not independently verifying these highly charged political claims, and we are not endorsing this specific political viewpoint. Our singular goal is to examine the legal mechanics and the strategic framework the author has constructed using intellectual property law as his weapon.
Understood, and thank you for the context. With that framing in place, let's examine the fascinating document included at the end of the compilation. It is a transcript of a chat log between the author R.J. Aguirre and an AI he refers to as his digital mentor. In this conversation, the author is not discussing the physics of the optical cable. He is discussing how to weaponize the patent itself. He introduces a concept he calls the double tag strategy.
The author's premise is rooted in market dominance. He theorizes that because the CVBNI technology is an absolute requisite for the future development of quantum computing clusters, every major multinational technology corporation, the cloud providers, the chip manufacturers, the telecommunications giants, will desperately require a legal license to utilize his patent. They cannot build the next generation of hardware without his intellectual property. The author intends to utilize this immense legal leverage to dictate corporate behavior on a global scale.
He wants to force these massive corporations to make a choice. He plans to offer them the commercial licenses they need, but he intends to attach draconian restrictive covenants to the contracts. Specifically, he discusses implementing clean hands clauses and anti-terrorism clauses.
The contractual mechanism is designed to force a geopolitical embargo. The author wants to legally stipulate that any corporation granted a license to utilize the CVBNI technology must categorically sever all business ties, direct or indirect, with targeted entities, which his strategy identifies as the Chinese government, its military apparatus, and affiliated technology conglomerates. If a U.S. tech giant wants to build quantum data centers using CVBNI, they must legally agree to stop selling their standard commercial servers, software, or microchips to the targeted nation.
My immediate reaction to reading this was intense skepticism regarding the legality of the plan. Can a single private patent holder dictate the entire international trade policy of a massive multinational corporation? If he tells a trillion-dollar tech company they have to abandon a massive global market, won't they simply sue him into oblivion under antitrust laws? Can't they claim patent misuse and argue he is attempting to establish an illegal monopolistic cartel?
The AI digital mentor in the chat log provides a highly detailed legal defense of the strategy, citing specific historical and future legal precedents. The core concept is the right of exclusion. A patent, fundamentally, is a government-granted monopoly that gives the inventor the explicit legal right to exclude others from making, using, or selling the invention. Historically, courts have upheld the rights of patent holders to attach significant restrictions to their licenses.
The text points to the concept of field of use restrictions.
Yes, a patent holder can license an engine technology to a company, but legally restrict them to only building lawnmowers, explicitly forbidding them from using the same engine in an automobile. The text extrapolates this right of restriction into the ethical and geopolitical realm. The AI cites the precedent of socially responsible or humanitarian licensing from the early 2000s. Major research universities would invent breakthrough life-saving pharmaceuticals. They would license the patents to massive pharmaceutical corporations, but attach strict legal covenants requiring the corporation to sell the drugs at cost in developing nations while maintaining high profit margins in Western markets.
It proved that a patent license can be legally weaponized to enforce an ethical or social boundary on a massive corporation. But the author's strategy goes much further than pharmaceutical pricing.
Which is why the AI mentor cites a more aggressive near-future legal precedent detailed in the text. The 2025 Copenhagen AI chip case. In this scenario, a court heavily upheld an inventor's right to sue a massive licensee for violating a no foreign end user clause. The court essentially ruled that an inventor retains the legal right to control the ethical destination of their technology. If a corporation agrees to the restrictive covenant to gain access to the hardware, they are legally bound by the geopolitical restrictions attached to it.
But the author is still a single individual going up against the legal departments of the largest corporations on Earth. If he tries to enforce this embargo, the tech companies will inevitably try to break the patent, invalidate it, or tie him up in endless litigation. This is where the author introduces his final and perhaps most brilliant legal maneuver. He calls it the bodyguard strategy.
The bodyguard strategy is a masterclass in exploiting federal intellectual property law to shield a private contract. The author knows he cannot survive a protracted legal war of attrition with a trillion-dollar tech conglomerate. To secure his legal position, he makes a highly calculated sacrifice. In the formal foreword of his book, and legally embedded within the patent applications themselves, R.J. Aguilar explicitly grants a perpetual, irrevocable, royalty-free, non-exclusive license to the United States government.
Why does giving the technology away for free to the government protect his ability to legally strangle the tech corporations?
Because it fundamentally alters the legal classification of the patent. By granting the United States government unfettered, royalty-free access to the technology that is essential to the future of quantum computing and national security, he transforms his private intellectual property into a federally licensed defense asset.
He essentially deputizes the patent.
Exactly. When a massive commercial tech company eventually attempts to bypass his clean hands clause, or when they attempt to sue him for patent misuse to break his embargo, his legal defense is no longer a private contract dispute. He legally frames their actions as a direct threat to the integrity of a critical national security asset. He aligns his private commercial restrictions directly with Federal Export Administration regulations.
He wraps his private vendetta in the American flag. If a tech company tries to sue him to sell quantum hardware to a hostile nation, he forces the Department of Justice to step in and defend the patent, because breaking the patent threatens the U.S. military's own quantum infrastructure. The government becomes his free, highly motivated legal bodyguard. It is a stunning manipulation of the legal code.
It really is.
So what does this all mean? We have journeyed through an incredibly dense, almost overwhelming spectrum of engineering and legal theory today. We started by looking at how a hollow metal retail shelf in a grocery store can be weaponized into an untraceable localized dead drop. We moved out into the urban landscape, examining how the legal protection of trademark yellow paint on a tractor can transform it into a massive noise-canceling pixel for a zero-emission satellite network. We broke down the computational nightmare of running 4D kinematic SGP4 algorithms to bounce radio waves off defunct weather satellites moving at Mach 22. And finally, we saw how a single engineer is attempting to restructure the entire global supply chain of quantum computing by intertwining spatial light modulators with restrictive legal covenants and federal defense licensing.
It is an exhaustively comprehensive portfolio of asymmetric architectures, but if we synthesize these disparate patents, a unified philosophy emerges. The author is articulating that in an age of absolute digital surveillance, where the internet is a compromised panopticon where every IP packet is inspected and the electromagnetic spectrum is constantly swept, true operational power no longer resides in the digital realm. It resides in the physical world, and it belongs to those who can see the invisible architectures of control.
Yeah.
The author demonstrates that the physical world, no matter how heavily monitored, is full of blind spots if you understand how to exploit geometry, physics, and legal frameworks. The power lies in redefining the utility of everyday objects. A metal shelf is a Faraday cage. A monitor pixel is a high-frequency transmitter. A piece of space junk is a passive relay mirror. A patent license is an international embargo. By altering the perspective on mundane infrastructure, you can build an entirely parallel, completely untrustable operational network right in front of the adversary's cameras.
It fundamentally changes how you perceive the built environment. And that brings me to a final provocative thought I want to leave you with today. Tomorrow morning, when you start your daily commute, I want you to look closely at the landscape. Pay attention to the massive construction crane idling in an empty lot. Look at the specific unusual angle of a sports car parked in a suburban driveway. Consider the landscaping crew arranging brightly colored mowers on a flatbed trailer. We now know, based on the rigid math and legal frameworks filed in these patents, that those mundane objects might not be random. They could be perfectly calibrated, geometrically aligned nodes in an invisible conversation, beaming coded operational vectors to a silent observer orbiting in the thermosphere. It forces you to wonder what other completely ordinary parts of your daily life have already been silently repurposed into an architecture of control that you simply haven't learned how to read yet.
The physical world is the ultimate encryptor.
Thank you so much for joining us on this deep dive. Keep questioning the systems around you, and we'll see you next time.